Hello, I'm Veronica Kovah, and today I'm going to talk about over-the-air Bluetooth low-energy hacking. I have been in the security field for many years, and in 2018, I wanted to do something that I had not done before. And I started a company and has been focusing on research in Bluetooth security. And today I'm going to share my story from knowing almost nothing about Bluetooth to find the remote code vulnerabilities in the firmware level. And first, I started the Bluetooth security by surveying the existing Bluetooth security researches. Then I read about Bluetooth specification, which is actually pretty large, but I didn't read all of it. I generally focusing on the length field and embedded headers that programmers likely make mistakes. Then I look for open source implementations because sometimes documentation was very vague. And for Bluetooth Classic, I couldn't find any open source implementations. But I found Zephyr and Apache JackBNimBLE that is a Bluetooth low energy open source implementation. But today I'm going to talk about mainly focusing on the BLE because that's the one that I has been focused on recently. And here there is a BLE stack, and there are many protocols. And for the dual chip configuration, these protocols belong to host. And these two protocols belong to the BLE controller. And the specification define how host controller interface should be implemented. Through the HCI, host generate HCI commands to BLE controller. And BLE controller generate HCI events to send back the result to the host. And when you receive BLE packets, it also generate HCI events to the host. And for this here single chip configuration, these all protocols will be located on the BLE controller. But for this configuration, the specification does not define how HCI should be implemented. So it is up to the implementer. They can use memory queue, or they can choose just not having an explicit HCI layer. But this talk, I will focusing on this link layer. When I started this research in mid-2018, there was literally zero controller-specific vulnerabilities. But now there are 14 of them, including a BT Classic and BLE vulnerabilities. Out of these 14, there are only 3 proven BLE RCE vulnerabilities. The first one you probably heard of is bleeding bit. And the 2 are the vulnerabilities I am going to talk about today. And let's see why an attacker is interested in finding these low layer vulnerabilities. Let's say an attacker found a PC-specific vulnerability. For this case, the attacker can only attack a single class of the devices. But if an attacker finds a vulnerability on this controller low layer, and this controller used for different classes of devices, he can attack PC, or he can attack car, medical devices, or IoT devices. And beyond that, this lower layer, in order to attack this lower layer, it does not require either authentication or pairing. the attacker just needs to be nearby the device. And I'm going to talk about 4 vulnerabilities on this low layer today. I prepared demos for the 2 RCE vulnerabilities, and I'll briefly explain 2 other vulnerabilities. But before talking about the vulnerabilities, I wanted to talk about how I set up my lab in order to start vulnerability hunting. And here is a development board. I recommend to start with the development dev boards because it's easier to actually find the vulnerability and make an exploit, because development board, in many cases, you can do the hardware debugging. But it's easier to finding a vulnerability and making an exploit compared to the end product. My lab has more than a dozen dev boards, but I'm just showing you these two of them because I'm going to talk about it today. And here's some serial converters. Just if you have some experience with the software development, it's just like a pre-nav. UART is the basic or the easiest way to debug our hardware. And I happen to have one here, the leftmost one, this serial converter laying around in the house. And I use this one, however, it does not have a CTS and RTS lines. And it took me for a while to figuring out even how to see the UART messages. So I do recommend, if you're getting the serial converter, get ones that has a CTS and RTS lines. And here is a hardware debuggers. Here 2 upper ones are for OpenOCD. But using OpenOCD, it requires slightly more work than the Sega J-Link debuggers. For the beginners or the hobbyists, I recommend using this Sega J-Link. For the hobbyists, you can use this education license. However, for the commercial, you have to get the commercial license. And since I'm a fuzzing dev boards, I had to have a way of power on and off these dev boards. So I used U-hub control, and then this here, the USB hub. So the fuzzer can turn it on and off my target. And when you generate the arbitrary BLE packet, there should be a way to actually look at them so you can confirm the packets are generated properly. I use the Ubuntu. This is very easy to use, and it has a very good display. However, it looks like the software has not been updated very recently, so it does not support newer Bluetooth protocol features. And luckily, this sniffer was introduced at the end of the 2019 at hardware.io. And sniffer does support newer Bluetooth specification, Bluetooth protocol features. And here's a Nordic device, and I use the Nordic device in order to generate the arbitrary packets. I start with the NRF52832. It's because the Zephyr and Nimble has a lot of documentations and examples using this device. That is because the documentation was written a while ago, and this one was an older dev board. The problem using this older one was, in order to use UART, I had to connect my serial converter to some of the individual GPIO. And it is kind of cumbersome when you move around this dev board. There's multiple cables coming out of it. So I end up using NRF5840. And the good thing about this board is it supports the virtual COM port, so you need only one USB cable. And with this hardware, you need a software. And today I'm going to release the JackBNimBLE. Using this JackBNimBLE software, you can generate an arbitrary BLE link layer packets. And it will be easy to extend to make your own fuzzer. JackBNimBLE comes into the two parts. The first one is the firmware. I made a modification to the nimble because nimble does not generate a package that violates the Bluetooth specification, but we do want to generate the package that doesn't comply with the specification. And in order to control this firmware, I made a host code here. And this host code is written in Python, and this Python code is responsible for making these arbitrary packets and give it to the firmware, and then the firmware will gonna send these packets. Now we have lab set up, then let's look at a specific chip. The first target is Texas Instruments WL1835 mod chip. And this chip supports Bluetooth version 4.2. And this case of development board was slightly different from other development board units in that it does not have hardware debugging exposed. And also in this chip, the BLE link layer is baked into ROM, which means the end product that use this chip will have same ROM contents as this device, this development board. And the host or the end product, in order to patch the functionality bugs or the security vulnerabilities, the host use a TI provided patch and redirect control flow into the different new code. And TI also provide some tools for the developers. And one of them is a HCI tester and logger. And what does this HCI tester does? I just mentioned about the patch file. And the patch file is in binary format. And if you use the HCI tester, this tool will translate this binary format to human readable strings. In the case of a logger, when I look at just the UART messages traffic, the UART messages actually is in binary format. And if you attach this logger to the UART, this logger will display log messages in strings. And we just saw this diagram. In case of this TI chip is belong to this dual chip configuration. And in the demo, you will see I actually generating some HCI commands in order to control this TI device. So now I have this development board, and I just need to start from this, just read one dev board. So I open this patch file using the HCI tester, and I could see there are many vendor-specific write memory because the patch file is to patch this chip. That means there can be a read memory, and I found a read memory in the one of the files that TI provides. And in the file next to this read memory, there was an opcode. I took that opcode and used the HCI tool, which is a Linux tool, and I could dump the accessible memory from this dev board. And one big step I could basically reverse this firmware better was after identifying these log functions. I mentioned about the logger. So this log function send these log messages in binary format to the UART. And based on this colors of the, basically looking at the colors of this log function, I could identify some of the function names and then some code context. And here's an example. When I just open the firmware, dump the memory with the IDA, there's no information because there's no symbols. But here, this function turns out to be one of the log wrapper functions. And the first argument is the log string ID. And after identifying these many log function log wrapper functions, I could see that this particular wrapper set the log level to 2. There is a level from 1 to 6, and it expects 2 parameters for the log format string here, because it expected 2 parameters here. And for the ID, once this function takes this ID, it adds 3580 to this number, and then figure it out. It needs to basically use this string. And based on this string, now I can see the function here name is this string, the perform command. And I made a IDA script to repeat this process. And now I have a lot of static analysis information. However, in many cases, this is not enough to actually identify the vulnerability or actually exploit the vulnerability. So I made a fuzzer. I mentioned about the JackBNimBLE. So JackBNimBLE is basically code that extracted from this fuzzer. And while I was generating arbitrary packet, and when I crashed the device, the information I'm looking at was not enough. And I will show you an example in the next slide. So I reverse engineered, read the hard fault handler code, and they found that there is a flag in the memory. If I set the flag, I could see way more information. And also, I have a way of hardware debugging. I can just check the register values or the memory values on the fly. But since I don't have that, I patch this binary in order to read some register values or the memory address values. And here's an example of the logger. Here, if I don't patch a binary at all, this is a default case, what you can see in the logger. And this particular case is why I was making the proof of concept code. And actually overwrote the PC value, which we're going to trigger the hard fault. And in here, just it repeats the similar information here, just repeatedly. So now I patch the binary. And let's look at the first patch here. And this one actually shows the just before stack buffer overflow occurs. And here, you don't need to worry about this log string here. I just pick a string ID that takes 2 parameters. This is the important information. So I wanted to print out what's the source address and what's the length value for the mem copy. And here, when I print out, it's a heap address. And please remember this one, because when I talk about the actual vulnerability, I will mention this source address again, and also this length value here. And I hook the code just before mem copy is called. And another patch I've done is I mentioned about the hard fault handler. And I set the flag to 1 so I can see more information at the time of the crash. So now I see all the register values and the stack information. And in the following, actually, there is a heap memory information as well. And now let's talk about the vulnerability that end to remote code execution. Actually, I found this integer on the floor very long ago. When I disassembled this firmware, I identified the mem copy first and looked around all the colors. And I could identify this integer on the floor right away, and which can yield to the stack buffer overflow. But at the time, I didn't have a way of just reaching this code path. So but after I'm making the fuzzer, I was able to crash the device, and then I could see the actual vulnerability can be reachable and exploitable. And guess what? This mistake is exactly actually same as bleeding bit, but in the different code base. In the case of bleeding bit, it was a heap overflow, but mine is a stack overflow, which means an attacker can exploit this more reliably. And let's see when attack actually takes place. A victim started scanning, then attacker here, it can just send a malicious advertisement packet. And as you see here, neither the authentication nor the pairing required. Just scanning and malicious packet, that's it. And now let's take a look at the assembly code. In this function, as you see here, the function allocate stack buffer space for hex to C. And the next is I actually skipped a little bit of instruction here because it was just irrelevant. This R6 value is a PDU length. PDU is like a packet data unit length, and then I will show you the format in the very next slide. It takes the length of value and subtracts 6 here. Here, there is an integer on the floor. If R6 value is smaller than 6, this end up R6 here becomes really big number. But next instruction is unsigned byte extension, which means it will eliminate the 3 most significant bytes and then leave only the least significant byte along here. And I want you to actually remember this part, why I'm emphasizing, because when I talk about my DOS vulnerability, this actually play a big role here, this instruction. And this R6 become here, length is a big number. It goes to the length field. And the next R1, if you remember from the previous slide, one of the previous slide, this R5 value has the heap buffer address here. Oops, let's see here. It goes to here, the source address, and destination address here is a stack address here. So you see there is a stack buffer overflow. And this is how this packet looks, advertisement packet looks like. This length field here, this is from the version 4.2. This 6-bit comes here, and which is the R6 value. And if I put less than 6, then there is an integer on the flow. And let's see why the programmer make those kind of mistake. According to the stack version 4.2, there are 7 PDO types, and all of them has at least actually 6 byte data here. So programmer can think as, okay, there is a packet length, I can just subtract 6. However, if it is a malicious packet, it can be smaller than the 6. Now, I started developing the exploits. But then the problem was because of the background BLE traffic, I could not control this heap contents. I could not control the heap contents well in order to make a reliable exploit. So I come up with an attack. It's a quiet place attack. There are lots of DOS vulnerability, including one of mine, and any unsuccessful attack can be a DOS attack. Let's see here, there is an attacker, and he wants to attack this BLE controller. But now he sees a lot of nearby BLE devices, and he wants to quiet them down. Then you can just kill all of them using the DOS attack. Then finally, this attacker can just send a malicious packet targeting this victim. Now, here's a thing. I'm not a real attacker, and I cannot kill the all neighbors' BLE devices. So my solution is, I had a bucket, a paint bucket. I made a Faraday cage out of this paint bucket. And here, in order to reduce the background BLE noise, this is the RF shielding fabric. And I wrap my these devices using the tinfoil. And I also actually, when I wrap these all devices into the bucket, I put the Ubuntu here in order to verify actually the background noise has been reduced. And let's take a look at the demo. I set up my JackBNimBLE here and I'm going to attack this TI device. Okay, now let's take a look at the next vulnerability. When I report the first bug to the TI, I actually made a POC that overriding the a program counter to the 41, 41, 41, 41. I thought this vulnerability, making the POC for this vulnerability would be just very simple. Just you're gonna be very similar to the first one, because when you see this code, the programmer's mistake is exactly the same. There is on the floor, which will gonna cause the stack buffer overflow. However, it turns out to be the manipulating the heap contents was a bit harder. So for now, it is a potential RCE, but at some point I'll make a POC for this vulnerability. The difference this bug from the first one is victim should be in the active scanning. And the victim will receive all this advertisement just like passive scanning. Then victim will generate the scan request in order to get more information. But at the time, the attacker can generate a malicious scan response. In the same case, it does not require either authentication or pairing. And here, this PDO type is 4 and length just need to be smaller than the 6. Now let's look at the next target. Next target is Silicon Labs EFR 32MG21 chip. I picked this chip because it supports Bluetooth 5 extended advertisement. And this development board also supports hardware debugging. And Silicon Lab provides an SDK, and this SDK comes with a Bluetooth stack in library format. And luckily, this library has some symbols. And this Silicon Lab chip is one of these single chip configuration case. So all these protocols reside on the controller device. So when I show you the demo, you will not see any interaction between the host and the controller through this HCI interface. And now I just started fuzzing extended advertisement packets. And but I ran into a problem because it turns out initially when I make the fuzzer, I initially use a Zephyr. But then this Zephyr turns out is not supporting the extended advertisement yet. So I had to change my code to use a nimble. And right after I fuzzing extended advertisement, I found a dose bug right away. Then I fuzzed a couple of days, but there was no crash. So I was wondering whether my fuzzer actually generating the package properly or not, and found that there was a case. I use the overtooth to see the packets, but overtooth does not support its extended advertisement packet or the very long length advertisement packet. So I couldn't see this, my generated code. So, but luckily there was Sniffle, which is supports the extended advertisement packets. So when I used the Sniffle, I could not see any of my packets. And it turns out when I debugged Nimble, and it turns out Nimble actually does not allocate enough time to send really long length advertisement packets. So I modified the Nimble, then I found a crash almost right away, which is to an RC bug. So before looking at the RC bug, I wanted to mention about my DOS bug, because I wanted to point it out that not every memory buffer overflow will end up as an RC bug. Here is a DOS bug. I want you to just focus this here a little bit. This R2 and R6, we're going to have a length value that is attacker can control. And since there is an integer on the floor, R2 value will become really big number. But the difference from the previous bug is, in the previous bug, there was an unsigned byte extension. Because of this really big number, 4-byte number, becomes just 1 byte. But this vulnerable code here does not have any of these before calling the memmove. So when memmove called with this big number, it will end up as a memory access violation. And the chances that the attacker can interrupt this memmove is really slim. So I call this bug as a DOS bug. Now let's move on to the heap buffer overflow, which is an RC bug. And explaining this heap, any heap buffer overflow quickly verbally is hard, so I'll give you a really big picture here. When this silage chip received a packet, it actually chopped into the smaller chunks, which is smaller chunks. Actually, length is weird. Actually, it's like a hex 45, which is an interesting number. And it maintains a chain buffer. While it's maintaining this chain buffer, a programmer made a mistake, and I could actually end up overriding a memory chunk boundary, and I could override this memory chunk's metadata pointer. And after that, I could override a function pointer, which is to a remote code execution. I report this one to Scilab on February 21st, and they fixed March 20th, which is very impressive speed. And let's look at the what attack packet looks like. Here is the this is the advertisement header, and this is the extended advertisement type. And there is a nested header here, and I could use this length here and to set to 30 hex 3C, which actually triggered some miscalculation. And if you want to know the details, please read my white paper, and the white paper will describe in detail. And let's look at the RC persistent demo. I set up my JackBNimBLE here, and this JackBNimBLE will send a malicious packet over the air, and we will attack the controller, and it will persist. Now I will briefly explain general Bluetooth security challenges. Just like most other embedded systems, it lacks common exploit mitigations. What it means is it is easier for an attacker to exploit devices in the wild. And also, chip vendors often do not support secure boot or secure reset. What it means is if an attacker successfully exploits a device, he can persist on the device. And what does it mean? It's easy to exploit and easy to persist. What is the impact of it? Well, it turns out it's very hard to assess the complete impact of any security findings. That is because it is hard to identify end product they use a particular chip. And also it is difficult to identify different classes of devices a certain chip is being used either. And just like any other businesses, the customer information is a secret. And it will be up to the vendor to notify any security findings to their customers. And even one worst case is an end product manufacturer may use a middleman, a package provider. In this, if there is this kind of chain, it is less likely this any security findings information is being propagated down this chain. So this is all time I got today. And for any additional information, you can check out at the GitHub in this URL. I want to thank Zeno, Rafael, and Marian for their valuable feedback. And thank you for watching my talk.